Great. I see that some people are done with the exercise. I will, what I will do is I will share my screen and we can solve it together. Okay, one thing that I should do is to, yeah, if I do, I will close. Okay, just checking. So I will share my screen. One moment. Mm, I don't know why it's not working. One moment. Mm, Okay, maybe I need to restart. I don't know why it's not working. 1 second. I will exit here, close. Mm, Okay, so maybe it works now. I will connect again. If I open the, I will see if that works with the, sorry. Mm, I will try to share my screen instead. Don't know what's happening. Can you see my? I don't. I don't see my. Do you see my screen or it's weird? I don't. Yeah. Okay. What I will do is I will restart my. I'll be back in a moment. I will think something weird with the web browser. Hi. I'm back. I'll see if now I can share the. Okay, since that it works now, let's see if I can make this. If I. Thank you. Seems that yeah, now it works. I wanted to use another editor, but hopefully is the font good enough? Is it readable? I hope so. So the exercise was we need to copy the memory from host to the device and then back and compare that everything works. So this is the template. What I will do is I will compile the exercise with make. So I will do make clean because I've been playing before with the make. So this is the way to compile the exercise. And now what we will do is we will submit the exercise to the GPUs. For that is sbatch and the script that is submit, I think. Yeah. So yeah, it worked. So to check the state, I will do seq minus minus me. And I see, yeah, the script took 4 seconds, and now CG means that yeah, it's like finishing the execution. Also, the name of the job ID is this one. So if I do ls, 36, yeah, this will be the. So if I do cat, I get the ROCm info, and I get the maximum number of threads per block, results, number of elements 256, and correct 1. So I need to fix that in order to have all the elements correct. So yeah, let's do that. Okay, I see in the chat that there is a message, a warning message. The warning message means that because if you notice here, I'm in this directory. I'm in /work, group ID, my username, and The way of moving to the work directory will be to you do cd. Yeah. If you execute that, I will copy that in the chat. If you execute that, you move from home to work. So in work, here what I have is Archer 2 GPU course. That this is I got it with the Git clone. Then I move to Archer 2 GPU course and section 2.1. Okay, so let's open the exercise. So the exercise has 4 parts here. Oops, here highlight. Let's see if I can, yeah. The part 1 is declare and allocate the device memory DX. Actually, let's go step by step. Let's do that. So here I can do double d underscore x equal null. So this will be the part 1. Part 2 is a copy host host array hx to device array dx. So to copy that, I will, well, sorry, no, it's copy, but because, okay. The part 1 is still not finished because it's declare and allocate. Actually, it's here in the to-do. So it's allocate memory on device. So here, if I go to the documentation, is to allocate this heap malloc. So it will be this. If I copy this line from the documentation, remember that we need to check the errors with the heap assert. So the vector will be dx. This will be the array length. Oops. Size of double. Okay, so this will be the first, the line, and also the part 1. Part 2 is copy input array from host to GPU. So for that, I need to do mem copy. That is here is the syntax is here. See if I manage to copy and paste. So remember again that we need to use a heap assert. Oops. Yeah. So heap mem copy will be we need to copy to dx, copy the contents of hx, will be array length, and we need to copy from host to device. Remember that this is I think it's called well, almost a common case. But yeah, each word is in a capital set heap. So main CPI host to device. So this is to copy the from host to GPU. And now we need to do the other way around, copy the result array back to the host output array. So what we will do is we will copy this line and we will paste it on edit. So it will be heap mem cp mem copy. Here we will copy h out, I think is the name of the variable. Yeah, h out. We will copy the contents of dx. Run late, and now we need to change the direction. So it will be device to host. Okay, so here I delete the to do because it's already done. This is already done. And now I need to free device buffer. That, if I remember right, is a heap mem free or heap free. Heap free. Sorry, I thought it was heap free, and this was dx. Don't forget the yeah, semicolon, and also here I should use as well like a heap assert in case that. Okay, so since that this is correct, let's check that. So let's save the file, and now I need to do make, and of course I have an error here. Here is because it seems that I forgot to. Okay, sorry. Is in okay, here I'm not closing. I forgot a bracket here, a closing bracket. So easy. Let's see. Yeah, now it works. And now let's submit. So with the batch submit. Is on the pending, so that's why PD. Let's. Yeah, seems that took only 2 seconds. So we have this output. Let's see if something happened. Oh, well, okay, it worked well. So now we see that the number of elements is 256 and correct 256. So it seems that everything worked well. Any questions regarding this part? Okay, see that there are interesting questions in the chat. Okay, we'll start with the end. The meaning of a heap assert is the following. If we open our file here, VI exercise, I think also Nano is available in case that you are more familiar, or in case that you are using with the mobile term, you can open with your local editor. But well, I'm using the inline because I cannot share the. I don't know why it's not working to share my other screen, but Nano, I think it works. Oh yeah, it works, but I will. Sure. Okay, it seems that heap assert actually is a macro that is defined here. The macro, what it does is calls that function, my error handler, and print in case that there is any issue, because all of the functions, heap malloc, heap main CPI, heap free, returns an error in case that there is an issue with the function. And here you see what it does. In case that is not a heap success, prints the line, the error name, error string, etc. So it's a way of handling the error. And in case that is, the error is fatal, exit the application. So this is regarding heap assert. Also, there is another question that is that there could be the case that you need to create extra data on the GPU and dynamic. Okay, that's a good question. In all cases that we have for some reason the data is on host, we need to copy that data from host to the device, to the GPU. In case that the data is generated on the GPU, you can always use heap malloc, but you will not need to use heap mem CPI, CPY, or mem copy. So it's not a problem. It's just pre-allocate the. We will see later that there are some we can give a hint to the compiler or to the runtime to tell them if the data will remain on the GPU, if the data we will copy the data back to the device. I don't see the issue. It's just allocating the data on the GPU, and the advantage here is that we don't need to do the memory transfer. That actually is the part that takes when you execute something on like a GPU, like some software on the GPU. This is the part that take most of the time. Copy in a small problems or small test cases. Copy data from from host to device and the other way around. So also in case that this is a small example too, but advice is try to minimize these operations. If for some reason you can generate that data on the GPU, please do so. No need to do that on the, let's say, on the CPU and then copy the data to the GPU. Not sure if that answers your question, but if not, please let me know. I'm happy to chat or understand better the specific case. Also, on the third day we will have a lot of time for exercises, so we can have a better look of that issue. Okay. If there are no more questions, what I will do is I will switch my screen to the theory. That is this window here. I will Okay, so we have seen this lesson here. Yeah, also that here there are like other exercises in case that you want to have a look at them. But we will move on to the, well, also this point, this is what I mentioned, that this copy here is quite time consuming. So if, yeah, one of the ways to optimize performance is to reduce this copy, or we will see later that we can how to say, yeah, make the copy at the same time do some calculations, like overlap is the word, overlap memory transfer and computation on the, like, in the host side. Okay, so let's continue with the, so next section is 2.02, that this is the executing a kernel. Because what we have seen so far is to move, we'll make this bigger, yeah. What we have seen so far is to move, to copy data from a host to device and the other way around. But once that we have the data on the device, we should, well, we are able to work with that. And this is what, here we have the concept of a kernel. Kernel is actually it's a function that we execute with the data that is already on the device. And yeah, normally, because the way of working of parallelize is we normally use a for loop. If yeah, you remember the exercise, we have an array, and what we will do in the next exercise is to work with the elements of the array. So to work with all of the elements of the array, we will use a for loop. We see an example here of a for loop in C. That, well, C, C++, yeah, similar, not to say the same syntax. So what we are doing with the array is we are multiply the elements by, well, actually no, we initialize the elements with the, yeah, 2 multiplied by the index. And as you see, this operation, let's say, is quite good or quite easy to parallelize because there are no dependencies. So we can execute, we can update all of the elements of the array in parallel. So that's quite easy, and actually this is a problem that is best, one of the best to solve on the GPUs, because there are no dependencies and the granularity is quite small. So when we use heap, or what, I think James already mentioned that this morning, but just as a reminder, you can always use, well, heap. Also, the concepts that we are learning here are pretty similar in CUDA. The way of working with that is we need to define the function that will update the array, and also we will need to call the function. That it is like a way to do it, let's say, using a heap. So the function here is this one. we add at the beginning of the function, we add a global that global means that this is a function that will be used on the GPUs. There are also, well, actually could be used, I think, on the GPU and also on the host. It could be the case that we can write a function that this is only to execute on the host, on the device. We can see later more about that. And here, rather than using a for loop, what I'm doing is I'm just updating the value of a resort, because in theory the function will be called in parallel and will be called if as many times as the elements that the array has. So that's why here we don't have a for loop, because we will perform as many calls of this will be executed in parallel. So we will not need to we will get rid of the for loop here. You will understand better when we do the exercise. The exercise comes from in the exercise we have a for loop, and what we need to do is get rid of the for loop and see if that works. Okay, so let's continue. So first step is define the function, that this is already defined. Second step is to call the function. So to call the function, this is the call. You may notice that there is a difference here. Here we need to specify blocks and threads per block. We have seen this morning that we can divide the threads in blocks. So here we see in the blocks we can have up to 3 dimensions. So, but here, because this is like a simple case, we will have just one block, and the threads per block also you see that are in 3 dimensions, but here we're using 1D. So we are using one block with the array length that I think in our cases, well, in the exercise was 256. So here we have a block, and each block will have 256 threads. So each thread will update a position of the array. And this is what that means, or what this is the difference. Rather than calling the function, we will need to define blocks, threads per block, and then call the function according to that configuration. Also, we need to make sure that we have enough threads to update the array, and also compare, because sometimes we will have most of the times we will have more threads than the size of the array. So this is also important to check on, and in case that there is a thread that doesn't have a corresponding position on the array, don't do anything, or don't modify positions in memory that are not also this this is like this struct that is let's see, 3-dimensional dim3 has x, y, and z. So blocks is three-dimensional structure, so yeah, as well as this one. It could be the case that in this previous example is quite easy. We have one block with that the size of the number of threads is the same number of elements in the array. But could be the case that also we could have more than one block. So the way of calculating the position of the array that I need to modify normally is that we will use that. We use the thread ID. In the X, because we are only in one dimension, we just use X dimension. And also multiply the block ID. That could be 0, 1, in case that we have 2, and the block dimension. So imagine that rather than one block of 256 threads, we could have 2 blocks of 128. So this will be like 128 multiplied by 1, in case that, and plus the thread ID. In that case, we will have we will update the result from position 0 until position 255. And a way of like updating that is we have this we can have this constant that is threads per block. As I said before, was 256. Here, for instance, if we want to use 2 blocks, we can use 128. The array length, that is 256 divided by threads per block. In this case, we will have 2 blocks. And we will do the same call my kernel. So by default, we choose a number of threads per block that, depending on the number of threads, could be like more efficient or not. There are some like ways to calculating that, but you can also use do some testing and see which block size is more performant. And once that you choose the number of threads per block, calculate the number of logs and launch the kernel. For simplicity here, we assume that the array length is exactly divisible by threads per block. But we will find the case that is not like that. That's why I said that we need to check that the result that I have here is smaller than is a memory that we have allocated, that we are not updating a memory that is not allocated. We will see better that with an example. And these are the variables that are internal variables that are accessible by the kernel, by the function that is executed on the GPU. So the grid dimension, block index, and thread index. And these names are reserved, and yeah, we cannot use them. Let's say that we cannot use them with another purpose rather than the GPU. Here, synchronization between host and device is because this is asynchronous. You launch the kernel, and it returns immediately. So the idea here is that there could be some cases that you launch something on the kernel. Sorry, you launch something on the GPU that is like let's say a different device, and then you keep working. You can do something on the host. So you have the parallelization that is done on the GPU, and also you have, let's see, like a device parallelization that you can execute something else on the host. Could be, yeah, most of the cases you don't do that, and you just call heap device synchronize. What it does is just is kind of a wait until my kernel is done. And once that the kernel is done, this function returns, and you can continue with the. Again, here, remember to use heap assert, and could be the case that there is an error in my kernel, so the way of getting that error is using this function. Okay, so this could before moving to the exercise, any questions? I know that this part is like all new. It's a little bit of rethinking how to do things compare that just having a CPU. But I imagine that doing the exercise, because the idea of the exercise is doing it step by step, you will understand better. So the exercise, the idea is what we do is in the previous one we have copied the vector or the array from host to GPU, and then from GPU to host, and that's it. What we will do now is a copy from host to GPU, perform our operation, that in this case is multiply the elements by 2, and then the result, we copy the result from the GPU to host. So the first step is to write the kernel of the prototype to perform the scale operation, and the second part will be to initialize the variables that we have seen here. We need to initialize threads per block X and blocks X. We can do it actually following this, We need also to define this, and do the call. I think if we open the exercises, also we can try with the different, with more than one blocks, than one block, sorry. And also we can change the array length and see if that works. So the exercise is in section 2.2. I think if the exercise is here, so I think I can open it. I'm just checking if the so it's already you need to do the call of the kernel here, and I think here on the top, somewhere here define the kernel. Here you see that you have a number of blocks and threads per block. Oh, well, this is just the handling. Okay, so I give you some time to do that. according to the, let me check the timetable. Okay, so we'll have 20 minutes to work on them, and, and then we will have a 15-minute break. Please, any questions, anything, let me know. We are a small group, so more than happy to answer questions. Yeah, I mean that's the idea of this course. Any questions that you may have, please share them in the chat or feel free to unmute yourself. Okay, I see in the chat there is an interesting question that actually yeah, I didn't. The question is inside the kernel if we can allocate memory. My advice is the kernel should be, let's see, only computation. So if you need to allocate memory, do that before calling the kernel. And in the kernel, yeah, should contain only computation, because if you do I never tried to do that, but I think if you I'm not sure even if that will work, but it will not be efficient. So the procedure is allocate the memory before calling the kernel, and the kernel, when you call it, all the memory should be allocated. Also, regarding the second question, sorry, didn't I just answer the first one. The second question is, can we perform recursion inside the kernel? In CUDA, I think it's possible, but not in a heap. If we go to the documentation, give me a moment that I think I can share it here. Actually, we'll copy that link on the chat. Here is explaining. I mentioned before global, and you notice that here we have also device, host, and here is the answer to your question. What you ask is called dynamic parallelism, and yeah, CUDA heap now doesn't support that, so kernel cannot be called from the device, must be called from the host. Okay, so what we will do is the section 2.03 will be, I don't think that it will be longer than 15 minutes. And from 3 to 4, well, we will have plenty of time to do the exercises. We'll have time to do the exercise that is in the section 2.02, and the exercise that is in the section 2.03, that is a little bit more difficult. And tomorrow morning, first thing, we will see the solution to these exercises. Okay, so let's continue. I will copy this link here, and yeah, let me share the tab. It will be yeah, this one. So now if well, when we finish the exercise that is in the 2.02, we will have a GPU program that moves data from host to device and do some operations like performs a kernel and then copy the data from device to host. Question here is about the performance. So what makes a code with a better performance or not? The first point is the parallelism that we can make on the code. You may be familiar or not with Amdahl's law that the law states that the parallel performance of a program is limited by the fraction of code that is serial. So that means if we can parallelize, let's say, only 10% of, imagine that we have like or the work time or let's say the work that a program does. If we can only parallelize the 10%, the 90% of the time will remain the same. So we can reduce the maybe 10%, but we will not get more gaining than that. So in that case, applying parallelism maybe is not, we will not have a great impact. But if the percentage is, for instance, 50% or 70%, 90%, we will see a big increase on performance, a big reduction of work time. So this applied to the GPU context means that which part we can execute on the GPU. If most of the workload can be done on the GPU, we will get like a huge performance gain. If the kernel, if we cannot execute on GPU that much, we don't, the performance gain will not be as good. So that's why also we should consider as well if the code that we have can be parallelized or if we'll get any benefits using GPUs or not. If we have a code that is, that let's say the part that could be parallelized is not that big, or if we don't have if the structure of the algorithm is not, let's say, suited for GPUs, maybe it's worth not, let's say, not considering them. I mean, there are some problems that are really good for GPUs, anything related with the machine learning, or at the moment I use a picture, a huge matrix, etc. But if you don't have that, performance gain could not be that good. Next concept here is occupancy. Occupancy here is we have talked about the threads, blocks, etc. And the number of cores on a GPU is way larger than the number of cores on a CPU. On a CPU, okay, if we use Archer 2, we can use up to 128 on a node, but the GPUs have way more than that. So in order to keep these cores busy, we will need a larger number of threads, a larger number of, let's say, chunks of work to keep the GPU cores busy. So to a GPU kernel, we will need at least around let's say the order of millions of threads in order to get like a good performance. In case that the problem that we can parallelize, for instance, the samples that we have seen so far, that we have a 512, 256, the performance gain using GPUs will not be that good. So yeah, maybe it's not like let's say a good idea to spend the time parallelizing the code on a GPU, because the performance gain will not be that high. So here where we have a two-dimensional sample that we have two for loops of and each one is the number of elements are 512, 512. So if for some reason, if for instance we launch a kernel that the kernel parallelizes the I dimension, the maximum number of threads that we will have will be 512. So this is not enough for a GPU. So the performance would not be good. But what about if we parallelize these two loops? We will have here 512 elements multiplied by 512 elements. That number will be like a 250,000 threads. In that case, yeah, that's better. So in that case, we have a way to use I mentioned before cores, so the CUs of the GPU. So this is an important concept. Here, the GPUs normally work with the fine-grained parallelism. So 512, each thread would be like let's say bigger or would take more time. So that's not. It's better to have 250,000 of threads that do a tiny operation. Also, here is a concept that actually this concept is a bit tricky to understand at the beginning, but once that you get it, it's easy. But yeah, in case that you don't understand it, please let me know, and I will be happy to repeat the concept. The concept is the coalescing access to memory. Let's say access the memory on following an order. Not you may know that if you have a chunk of memory and you do random accesses, like first accessing the position 0, then position 512, then position 50. This is not efficient. It's efficient when you access the memory in a linear way, let's say. So for instance, if we have this matrix, it is better to, for each element, if I iterate through J here. If we do it the other way around, we will for the cache, we may have a lot of cache misses, and that will not work. This is like an advanced concept. I'm not sure if you are familiar with the let's say performance on memory accesses. For GPUs is the way of accessing memory is quite different. Rather than accessing an element one by one, as it's done on a CPU, you will. Sorry, one moment. Rather than accessing one by one, you will access the memory on waveforms of consecutive threads. You may remember from the morning that we have groups of threads. So a group could be can say 32 or a block. So this block, each thread performs a memory access in parallel. So rather than accessing the elements, let's see one by one, we will need to iterate in the iterations will be the size of the block. Now I will share a picture where we see better that concept. But the thing is, for instance, here, if we iterate through J, this is not this is efficient. Let's see, from the CPU point of view, from the host point of view, but if we use GPUs, we will need to iterate through I, because elements in J will be accessed in parallel, because the way of execution on a GPU, rather than executing, let's see, element by element, you execute blocks of elements at the same time. So it's a kind of if you know vector operations is like a vectorization. You do it like in one call. You do this for each element in J. You will do each thread will perform the operation. So in that case, for instance, it's better to iterating using the I rather than J. Let me share with you this. I will share in the link. So I found this in the. Oh, sorry, we stop instead. So what I mean is the following: if we have our matrix here, and you see the index is here, that we are iterating using J. So we have 0, 0, 0, 1, 0, 2, 0, 3. And imagine that we have a block of 4 elements. So because each block is executed in parallel, so thread 0 should have this element, the thread 1 should have this element, the thread 2 this element, and the thread 3 this element. And this is executed at once. Now, next iteration, you will execute these 4 elements in parallel. And you see here that what it changed, the thread, the index of the thread is the same that the index of J. But you are iterating using I, using the row index. So this is done in parallel. The yellow elements, let's see, red elements in parallel, blue and green. So this is a coalescence memory. The other example that doesn't work is if we do it in that way. If we iterate using J, in iteration 0, the thread 0 will load this element, the thread 1 will load this element, thread 2 this element, and so we are getting access to memory that are not consecutive. This is for the iteration 0, for iteration 1 as well. Well, here we have a small example that actually the whole example could fit in cache and to be fine. But at the moment that we have a bigger matrix, we will have a lot of cache misses, and yeah, this will not be efficient. So here is takes a while to, and I think these pictures show better that we should use the outer loop, so we should iterate through rows rather than through columns. Is that clear? So we should follow this. So the next exercise will be, is to play with the issue of parallelism and occupancy. So we have a code, and what we will use, actually here we will use a profiler that is called RockProf, and with the RockProf we will see the work time that or the time that the kernel took to execute. So we will launch the exercise as it, and we will see our kernel how long it took, and we will do improvements on the kernel, and we will measure them, and we will compare the time that the kernel took. So now you have two exercises, the exercise of section 2.2 and the exercise of section 2.3. Yeah, I'll be here until 4 p.m. So any questions or anything, please feel free to let me know. I will be more than happy to help.